Hey Providence Engineering Academy, I hope your week is going well. We're going to keep right on. This is week 3B and the pages to read are listed in Google Classroom, starting at page 51. So I'm going to do a little bit of review, a little bit of strengthening what we already did, and again we'll see if we can get this done in less than the 55 minutes. To start off with, I want to tell you a little story. Let's see if we can do this. Let's say you live on a typical city block area. I'm just going to show it like this, and let's pretend that the blocks are all very uniform. They're each 50 meters long. Okay, 50 lowercase m. Make sure you make it lowercase. They're all squares, so they're the same in both directions. And let's say you start from this location right here. This is your home, and you are going to walk to your friend's house, and your friend lives right over here. So when you get to your friend's house, there's obviously, I guess you could probably say there's an infinite number of ways that you could get there. You might go up, make a turn, go across, maybe you make another turn, or maybe you don't, maybe you keep going. But you can see there's many ways, many paths that you could get to arrive at your friend's house. Okay, you could have also just gone straight all the way across, then straight all the way up. So the question is though, how much distance did you travel? If each one is 50 meters, how much was that? Well, I hope you can see that it is going to be 7 times 50. Okay, I'm just kind of counting up each of those little street segments. So I can say pretty confidently you traveled, with the path that I drew right here, 350 meters. Okay, that could have ended up being more. If you had looped around, what if you did something like this? You might have gone up, across, and then down, and maybe this way. That would have got you there. In that case, let's see, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. Okay, not very efficient, but maybe you had some errands to run. 650. Okay, almost twice as long. Those will be good. Now, I think it's safe to say you can't get there in anything less than 350 meters, but that's the distance that you traveled. Now, my next question is, what is the displacement that you traveled? And we talked about this last time, the difference between distance and displacement. Distance is a scalar, always a scalar, has no direction associated with it. Displacement is always a vector. Okay, that is what those two words mean by definition. You can't use them interchangeably. Displacement refers to the vector. In the book, it uses the phrase "as the crow flies," which I think you know, as the crow flies. And so what we're talking about when we say displacement is this straight line with an arrow. It is actually a vector. So you have to show the arrow, the shaft, the tail, the point of application, all that. So what is the displacement? Well, we could at least work out what the magnitude of that is right now. You can see, maybe you can see, hope you can see. Let's switch over to green here. This is a right angled triangle, and that really helped me out there. I don't know why it took over the blue. Put that back. Is a right angled triangle, and that means we can use the Pythagorean theorem. I'm going to say that the, if a squared plus b squared equals c squared, there's your Pythagorean theorem, then that hypotenuse c, we take the square root of both sides, and the a in this case was 200 meters, okay, 50 times 4, and the b in this case is this one here, that is 150 meters, 50 times 3. There you go. And you go and get your calculator and you work that out. 200 squared. I'm doing this on the side, you can't see that, but I promise you I am. Come on. And that is going to be, I got 4,000, wait a minute. See, this is why I don't actually like this calculator I have. I'm going to have to get a better one. You've really got to pay attention to how your calculator thinks when it comes to order operations. Mine does not think well. 250, that's what I wanted. Okay, this is 250 meters, and yes, I did choose numbers, which would give a very, very simple answer. Okay, 250 meters, no decimals required. That is the magnitude of the displacement vector. Now, I didn't actually give a name, like a label to this displacement vector, so that's why I'm not showing any of like the absolute symbols or anything that I talked about last time. But I think that is just one quick little reminder of the difference between displacement and distance. If you were a bird flying from your home to your friend's house, you would fly 250 meters. If you walk the distance, it could have been anything from 350 meters upwards. But distance and displacement are not the same thing. Now, on page 54 in the textbook, they start talking about something which, again, we did mention already, and that is delta notation. Okay, delta notation. The delta that we are using in this course is the uppercase delta, which is drawn as a little triangle. Okay, the capital letter D in the Greek alphabet, and we said that delta means it is a measurable change in something. So if you see delta x, it means what was the measurable change in your x position. If you see delta capital T, it means what was the measurable change in the temperature of something. Okay, it's always referring to like a, well, I shouldn't say always, but it's often referring to like a passage of time has gone by, and what was the change in something. You can have delta V, what was the change in your velocity, and by the way, delta V is the same thing as acceleration, lowercase a. Little bonus there for you. But let's use some delta notation here. So with our city block walking situation, we could say this. We could ask questions like, all right, let's, well, I guess we need to first define that this is the x direction and this is the y direction. Once we do that, just like a typical Cartesian plane, we introduced that term last video, Cartesian plane, named after René Descartes, XY coordinate plane. Once we set that up, now we can ask, or we can give answers like, what was delta x? What was the change in x? What was the measurable difference in x? And think about that. What's the number? Say it in your head. Say it out loud. It was the 200 meters. Okay, the 200 meters down the bottom of the screen, that horizontal distance, that was the delta x. That was the change in x from home to your friend's house. You know where I'm going next. Delta y is 150 meters. Okay, that's that vertical 150. It's not really vertical, I guess. Maybe it's like northerly or something. We're looking top down. So, but you know, according to the coordinate system which I created, it is 150. Interesting point to make here on something. If you now turn around and you travel back to your friend, sorry, back from your friend's house to your home, you go the other way, then your delta x would actually be negative 200. That's to signify that you are going in the backwards direction. Okay, as soon as you have labeled this whole like x and y coordinate system, you've just assigned direction to things. You've said this is, I didn't really say it explicitly, but you could, this is the positive x direction. This is the positive y direction. Okay, so you've just given direction to things. You've given a sense to things. Another word I like to use is sign convention. But yeah, so if you turn around and go from friend's house back to home, you've just gone delta x negative 200 meters and delta y negative 150. Okay, so deltas do include the idea of direction or sense. Okay, now I said already that I don't really want to get too much into 3 dimensions. And part of the reason is that it's just plain tricky to draw those diagrams. If you look on page 53, you can see there is a 3-dimensional diagram, and it's just got a lot going on. It is hard to draw them well. The author of this book is clearly using you know, computer software to create pictures, which of course that's what everyone does now. But it is hard. It's hard to sketch by hand. With practice, you can do it for sure. But you know, it's ripe with challenges for most people's drawing ability. And so that's part of the reason why I want to avoid it for the most part. But I think today I will just include the ideas, and we'll get into that today. But don't expect very much in the way of 3-dimensional vectors from me. But since the principles don't change, I'm just going to touch on it today. I actually really like the way that page 57 lays it out. Page 57 gives kind of a very general way in which you can draw 3D vectors. And don't forget, the reason why it's so hard is because we're trying to draw 3D things on a 2D surface. That's why this is tricky. 2D drawings on 2D paper are great. 3D drawings on 2D paper, you have to, you know, imagine things. You got to, you know, approximate things in some ways. And so I actually really like how we can. I'm actually going to slightly modify it there. Drawing, going to give it kind of double perspective, if you like. It's really a good idea to draw what we call a bounding box. Okay, a bounding box. And if you didn't just draw that into your notebook, you should copy that down. It is so good to get the practice at drawing things like this. You'll notice that all of my vertical lines, here they are all truly vertical. You'll notice, well, I didn't do a fantastic job. Maybe I can do a little better actually over here. I was about to say, you'll notice that all of these lines are all parallel to each other. Okay, it's all about keeping things parallel. You see I've got 4 parallel lines, like one here, 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 and then in the back, the dotted one. And then these ones here, here. Whoa, I don't like that at all. Get rid of that. You know, here, and this dotted one down here. Those are all parallel to each other. That's a reasonably well drawn bounding box. The dashed lines or the dotted lines, those are the ones that are kind of behind, they're like hidden lines. Okay, and we can do this. You know, we can draw like all sorts of diagrams really like lend themselves to this idea. Even when, you know, things get more complex, maybe you're drawing like a machine part or something, it's a good skill to be able to draw, to kind of imagine where those lines would go, you know, even like circles and things like that. And it just comes with practice. But yeah, that's a good skill to learn. All right, forget that one. That was just for the fun of it. Oh, apparently those ones won't be deleted. Here we go. Here we go. Okay, so we pick one corner, and I'm using the exact same as the book, and we call that like that's the tail of the vector. Maybe I will use, yeah, I'll use a different color. Make it a bit clearer. And then the head of the vector is always going to be the opposite corner or the opposite vertex of the box. Okay, so you're always picking two opposite corners, like two vertices that are as far away from each other as they could be. Those are the tail and the head with the shaft connecting across them. Okay, so you really have to imagine like this cube in front of you, an actual cube or an actual prism, and then there's like this line, this arrowed line that's strung out between the two. Okay, maybe in your room, in your little office space, maybe you have some kind of cube or like a, I don't know, like a block of Lego or a paperweight or something that's nearby, and you can imagine that stretched out. Okay, so that, I'm just showing this to you as a really handy way to draw these. And generally what we really want to know is what is the magnitude of that vector. And the magnitude in his diagram is the E, okay? E. And also, I read on page 56 that this author uses italics as another way to show magnitude of a vector, as well as the vertical lines on either side. So he could have done that, okay? But he's chosen to do it in italics, and it's hard to accurately show italics, but that is what he means. Okay, this is his way of showing the magnitude when you see that. That's good to know, huh? Now, if you want to know what the magnitude is, it's very much still the Pythagorean theorem. Just because it is in 3 dimensions, the Pythagorean theorem, that's the theorem with an EM, it still works. It is still the method to use. Okay, we know that with 2-dimensional things, we have A, B, C, and actually, yeah, I think I'll do a more standard, slightly more standard convention is to use lowercase for sides in geometry. So we know, we've been saying it already, Pythagorean theorem, you know that. But the Pythagorean theorem still, it holds here, but it also still holds in the 3D situation. And all you have to do that's different is now you have one side of that bounding box, like the length, let's say, the other side of that bounding box, the width, and you have a height of that bounding box. So we've kind of messed up like the a squared plus b squared equals c squared because we just used c for one of the, you know, parts of that box. And this author uses E as that final resultant vector that strings out across. So we'll use the same thing. I'll also use uppercase for this one just because that's what he uses for his too. But he is saying that if you want to know what it is, it's the same idea. Instead of squaring the 2 sides like we do over here to get the square of the hypotenuse, now we add together those 3 squared sides. Okay, there's just now 3 terms instead of 2. And then we take, again, the square root at the end. So the transposed version of this, just like I've been transposing the two-dimensional Pythagorean theorem recently. And gee, look, sorry, I should have foreseen this. Let me do uppercase so it's all correct. Just like in his book. There we go. So you take the square root of the sum of those three squares, and that gives you the resultant magnitude. And when you heard me say sum of those three sides, I hope that you might have even had the word sigma pop into your head there. You could describe that with sigma notation. Okay. Now I want to show you something else that I chose to not assign this to you as textbook reading, but it is a very, very useful notation, and I want to give that to you today. So if you want to go and read through it, it's on pages 59 to 62. Okay, 59 to 62. But I'm not requiring it. That's why I did not assign it. It gets a little complex, so I'm going to give it to you in summary form in this video because it's just too good not to. And it's that if you want to show a vector in a readily accessible equation form that avoids having to draw a diagram perhaps, or is like an alternate to drawing a diagram, there's something called I, J, K notation. And the I, J, and K here, they are all written in lowercase, as you can see. And they all have what is called a hat symbol, H-A-T, just like the chapeau, the sombrero, okay? A hat. Thing you put in your head. And I, J, K corresponds to X, Y, Z. Okay, they have the same directions, the same positivity, negativity. It's the exact same idea. If you want to get into the details of it, I, J, and K actually stand for something called a unit vector, and the book describes what that means. It's like a little vector of length 1 that points in the direction of those three directions, X, Y, Z. You don't need to worry too much about that because I think the idea itself is pretty intuitive, but if you have that three-dimensional vector again, okay, that went from there to there. Let's say might not have been the best one to do because it kind of lines up with that upper line, but that's okay. So let's say that this was, let's just give it some numbers. Let's say that was a length of 4, maybe that's a length of 6, and maybe that's a length of 3. And let's label that with E again. So first of all, if you want the magnitude of E, you're going to add together that. And let me do that on the side if you'll give me 1 second. X plus 9 equals 61. Square root of 61 is about, let's say, 7.8. Okay, 2 significant figures. So, and this diagram is roughly to scale, maybe roughly, very roughly. But a way that you can show this vector, okay, and now notice I'm putting the little vector symbol above it to show that I'm talking about the whole vector, not just the strength of it, not just the magnitude of it. You can show it with this I, J, K notation. Here's how it works. You say how much it is in the X direction. Okay, I guess I'm implying here, I didn't really say it, but I'm implying that this is X. You say plus 6J. Again, this would be implying that Y was that axis out there. And then plus 3 k. And that is the z, or the vertical dimension. Okay, so this diagram and this line right here, those give all of the same information as each other. Okay, no more, no less. Everything you could need to know about that vector is contained right here, just in numbers and variables and unit vectors. Okay, without having to draw the bounding box and the XYZ axes and all of that kind of stuff. Okay, so it's a really, really, really handy way to do that. It also means ultimately later on you could do math on vectors. And you know, I just heard from Ava Kilper's mother. Ava graduated and went to do engineering at Oregon State, studying robotics, mechanical engineering, and she just finished her first vector calculus course. And I took vector calculus, you know, back in, you know, the early 2000s, and yeah, like you need this symbology, this nomenclature to do vector calculus properly. That's why this is so important. So all that's way down the road, but I want to show it to you because the basic idea of writing the x and the y and the z directions, that's easy enough to understand, I think. Okay, if you do it in 2 dimensions, that's even easier. So let me give you that 2-dimensional situation. You know, again, you might have, here are your simple axes. I don't know why horizontal lines are so much harder to draw than vertical lines, but apparently they are. You might have this vector, again, that starts at, that starts at 0, 0, and maybe goes to the point 4, 3. Okay, you have a vector that strings between those, just like that. And let's call that vector f. Okay. So you could represent vector f without having to draw that diagram by doing this. You could say, look, this thing is like 4 units horizontally. So we do 4i. And this thing is 3 units. Okay, it's the same 3 as what's right here. Same 4 as what was right there. Plus 3j. Okay, so again, this here contains all of the information as in all of that. That's why it's so useful, so powerful. It's more compact. It's completely understood by everybody the world over. So super useful. Now here's a little question for you. What is the magnitude of vector f? You can pause the video, you can work it out, or maybe you just know that straight away because you're so incredibly brilliant. We are just going to take the Pythagorean Theorem, or you might even know, you might remember that 3, 4, 5 is a Pythagorean triple. That will work out to be 5. The magnitude of this vector f is 5 units. Notice I don't have any units of force or meters or anything like that because it's just a mathematical thing we're doing for this question. All right, here's the next thing. Sometimes, in fact oftentimes, instead of being given the like delta x and delta y, or like the xness and yness, the horizontalness and verticalness, and then building the vector from there, very, very often we are given the magnitude and angle first, or magnitude and direction, or magnitude and sense. We're given those first, and then we have to work out from there how vertical it is and how horizontal it is. How much I, how much j, how much left, how much right, how much up, how much down. So very often we'd be given a vector to begin with a reference line and an angle, maybe it says 70 degrees, and maybe it is 80 newtons. Okay, there it is. Maybe I'll give a point of application as well. So we have the magnitude, 80 newtons. We have the angle, 70 degrees up from horizontal. And so that's fully defined. But very, very often we now want to go back and be able to say, what is this amount? And maybe I can, if you don't mind, I'm going to call that delta x. How much x distance is there? How much, or x force? How much delta y is there? Okay. How tall is it, in other words? And like everything I'm saying over this whole week, and everything in the textbook is all just these same ideas over and over again. We're just trying to show you all the different ways we can approach this, the different notations, but I'm not giving you anything new here. All we need to do is just create that wonderful little triangle. No. That wonderful little right angle triangle, and we've got to use our sine, cosine, or tan functions to work out what those side lengths are of that triangle. So if the question is, like, how up is this 80 Newton vector? Well, we're going to think about this and say, all right, we have a reference angle. It's the 70 degrees. Therefore, because that's the 70 degrees, this leg must be the opposite side. This leg, nope. This leg must be the adjacent side. This is, of course, always the hypotenuse. Never changes. And then we're going to decide which of our sine, cosine, or tangent functions do we want. Now let's start with this one, with the x. So if I'm dealing with the adjacent and the hypotenuse, because I know the hypotenuse already, the a and the h is going to be the a and the h are right here, okay? That's the only one of these three out of SOHCAHTOA which has the a and the h together. So that is going to drive me towards using cosine. So I write cosine of the reference angle equals the adjacent over the hypotenuse. And by the way, it has to be adjacent over hypotenuse because the a and then the h were right here in SOHCAHTOA. Okay, that's why it's that, not the other way around. And we work out what cosine of 70 is, which is done on your calculator. And the answer is it's about 0.3420. 4 significant figures is a good safe number. Remember that. That's what our textbook holds to as well. So that means the ratio between the adjacent and the hypotenuse is 0.3420, or about 34%, in other words. And let me actually go one extra step here. I'm going to replace the words adjacent hypotenuse with what is actually in my diagram. Because I put delta x, like the change in x, the measurable change in x, I put that down the bottom, and I put 80, because 80 is the length of the hypotenuse. So I have this equation now, 0.3420 equals delta x over 80. Now, delta x, by the way, think of that as just one thing. Delta x is a thing, just like the letter y, or the letter t, or the number 30 or something in an equation. It's just one thing. Now I'm going to solve this equation for delta x, and I do that by multiplying 80 onto both sides. And now mathematically, this is exactly what I was doing the other day. I'm just choosing to keep it in like good, proper algebraic form. Let's say, let's round off a bit here. Let's say 27. 27 units is delta x. And you know what? I should probably just put the units on here because it was a unit question, 27 newtons. Now for the opposite side, the delta y, opposite and hypotenuse, that's right here, that particular combination. So I am going to need to use sine. Sine of 70, I'm using the exact same reference angle, is the opposite of the hypotenuse. Again, O and then H, because it is O then H in SOHCAHTOA. Sine of 70 degrees is 0.9397. And now again, I'm going to substitute what is actually on my diagram. That opposite side is labeled with a delta y. So okay, I'm going to use that. The hypotenuse is labeled with 80 newtons. All right, I'm going to use that. I now solve the equation by multiplying both sides by 80. And that again is the time when I pick up my calculator and I get 75 rounded off newtons. Okay, so I now know everything I need to know. I've got 27 newtons here. I've got 75 newtons here. And by the way, you could check that your answer is correct, because if it is, this is a right-angled triangle, and the Pythagorean theorem should hold, right? That relationship should be true. Let's see how well we did. 27 squared plus 75 squared. I hope you got your calculator and that you just automatically do this, is 6,354. 80 squared, probably know what that is, just mental arithmetic, 6,400. Why do those not end up exactly the same? Who can tell me? You probably all could, but I can't hear you. So the problem here is that we chose to round off right here and here. And because we rounded off to two significant figures, because that's what the original question was given in, we did kind of lose some information out of it. However, notice this. If you change 6,354 to be two significant figures, you get 6,400. 6,400 is already in two significant figures, so we don't need to change that. Whoop, having a hard time here. There we go. So if you stay to that two significant figures, it does actually stay correct on this one. It doesn't always perfectly work out like that, but that's all good. Now, I went to two significant figures where I've marked with the two red stars because I kind of thought that was the end of my working. And it's at the end of your working that you clip off, that you round off. I wasn't expecting to go ahead and do more calculations with those numbers. So that's why it got a little risky. So yeah, I've always said the whole way, only go down to significant figures when you think all the working is done. Otherwise, keep as many as you can, just keep it on the screen in your calculator. Don't clear the screen every time you do an equation on a calculator. That's a bad practice. Okay, we're doing well. What I'll also show you, just to wrap this one up, is that we could now take this vector and we can now write it with the I, J, K notation, or rather in this case I and J, because it's only two dimensions. So what you would do here, you would say this vector is described as 27I plus 75J, and then you put the unit right at the end all by itself. Okay, 27I hat plus 75J hat, and then you put the Newton at the very end. And again, I love this notation because it actually contains within it. It contains within it the idea of the 80 newtons, because that's the magnitude of that triangle you've just described. And it also contains within it the 70-degree angle. That is not immediately apparent, but it's there in the trigonometric relationship. And it's also a good thing to point out that both ways of describing the angle have exactly two pieces of information. Originally, we described it with a direction and a magnitude. That's your two-piece information. But then we turned it into IJ notation. That was also two pieces of information. We said, how much to the right is it? That was the delta x. And we said, how much up is it? That was the delta y. But it's still two pieces of information, because that's how much you need to define a vector in 2 dimensions. In 3 dimensions, you always will need 3 pieces of information, either IJK numbers or 2 angles and a resultant magnitude. But we're not going to do that, I don't think. All right, I'm going to give you one more exactly like that to practice with. And this is where we're ending it today. I'm just going to mess around with you a little more. Let's say a vector that looks like this. A little longer. Let's do this. Let's make this one 500 pounds, and let's say 25 degrees, just to be a nuisance. Okay, now this one's a little interesting. This one's pointing off to the left as well as pointing up like the last one was. Vectors can point up, down, left, right, any combination of all of that. Let's go through now and describe the horizontalness and the verticalness of it. So you got to start by visualizing that right angled triangle. Okay. And we have a delta x, like a horizontal change, and we have a delta y, a vertical change. And we want to know what those are. So you're going to walk through those same steps. You start by picking a reference angle. And when I say to pick a reference angle, I'm stating that step as a formality. It's very, very obvious that we'd want to use the 25. You don't have to use the 25. You could, at any moment, you could choose to use the other angle, the complementary angle, which is 65 degrees. But, you know, why would you? I'm going to take that away so as not to complicate things. And now you're going to go to your SOHCAHTOA. Well, actually, let's label the sides. So because we chose that as the reference angle, that means this now becomes the opposite side. That becomes the adjacent side. This is always the hypotenuse. And so we're going to do this. We're going to say, all right, let's do sine of the reference angle is opposite over hypotenuse. Sine of 25 degrees, I do that off to the side, is 0.4226. The opposite side has been labeled as delta y. And by the way, we could use other labels. I'm just going to keep using the delta notation because I likes it. And 500 was the hypotenuse. We solve that equation now by multiplying 500 onto both sides. Get my calculator. Bang, 211. I'm going to use 3 significant figures. And that is in, I may as well put pounds here because I know the answer is in pounds. I can label my diagram, 211 pounds. I'll do the other side. Cosine of 25 equals adjacent over hypotenuse. cosine of 25 is 0.9063 equals delta x over 500. Multiply 500 onto both sides to solve the equation. 453. 453 pounds is the answer. Okay, I wrote that differently last time, that's okay. 453 pounds, so I will label that right here. 453 pounds. Okay, and we could, once again, we could confirm that. We could say, are we absolutely sure? It's 211 plus 453 squared. Does that really equal 500 pounds, which is what's that? 250,000. 211 squared plus 453 squared equals 249,730. Now, if I round off to 3 significant figures, then I get the same thing. And yeah, all those numbers there are correct 3 significant figures. All right, so that worked out pretty well once again. And if we're going to write this in IJK notation, we're going to say it like this. We're going to say negative 453i plus 211j, and then the unit, which is in pounds. So there is a final representation of that. I hope you have a question right there as I did that. Hoping that you're wondering about that negative in front of the 453. Why is that negative? Well, it is because this vector is pointing to the left. It's pointing to the left and up. And the basic, typical, standard directions that we use are the same as for XY axes. Okay, positive I hat is over this way, negative I hat is over this way, positive J hat is up, negative J hat is down. So because this vector was pointing leftish and not rightish, because it was pointing upish and not downish, that's why we had the negative here, but the positive here. Those negatives and positives are incredibly important, and I hope that makes sense to you why I picked them. It all comes down to this basic direction right here, which is exactly the same as what X and Y have always been for you. That's why I think that's going to come pretty easily. Okay, we're going to finish it there. Be proud of yourself. Be very proud. You are doing first year college material out of a first year college textbook, and I'm intentionally taking you a little further, a little more challenging than what we will really be using in practice most of the time. The reason why I want you so familiar with these vectors in statics, it's basically for one reason. It's that we're going to apply forces to objects, and we need to be able to calculate what those total forces are going to be, and then of course what they will do after that. If you go and study things like dynamics where things are unbalanced with their forces, a whole lot of other sorts of fields of study as well, you'll also do vectors, and you'll need to know how those work too. And part of the problem is that you have really been speaking in terms of scalar numbers your whole life, except for the older students. So scalar numbers are how we naturally tend to think. It takes practice to learn to assign direction to numbers. I guess when you add and subtract numbers, positives and negatives, that is a direction of a sort. It's a direction on the number line, but that's a very, very constrained direction. That's like a one-dimensional direction, just forwards or backwards. But now we need to bring you into the 2D and the 3D world even, where direction can go anywhere and do anything. Okay, we're liberating you from the number line, but we got to show you how to work with it then after that. So it takes some time to understand. Once again, I'm going to remind you, please try to answer someone else's discussion board comment if you can, because there's no better way to learn than to teach someone else. All right, thank you everybody. Enjoy the rest of your week.